Good morning, students. Welcome to the lecture of Operation Research. In the last lecture, we have seen some important theorem which tells us that the min-max value is greater equal by max mean value of the game. Also, we have seen a strategy for finding the rectangular games without saddle point. Okay, whenever we have a saddle point to the given game, it automatically gives us the optimal strategies and the value of a game. Actually, this will be a case of pure strategy. Pure strategy means a player knows exactly which activity or which strategy will be played by the other player, and he chooses to play one activity at a time. But in case of games without saddle point, there is an example we have discussed. No? This is a 2 by 2 rectangular game. We here the saddle point do not exist. Now in these type of examples, in these type of games, one has to determine same when one has to use the same strategy of finding the maximum among the minimum gain and minimum among the maximum losses. But instead of selecting one activity or one strategy at a time, a player chooses to play both activities with some probabilities. A player chooses to play all the activities with some probabilities. And whenever we are involving the word probability, we know the two properties carried out by the probabilities. What are the properties? Suppose the player A chooses some m activities to play with some x1, x2, xm probabilities. All the probabilities should be non-negative and sum of probabilities must be equals to 1. Now, as we don't have exactly an idea which activity will be selected, therefore, instead of finding the maximum among minimum gain, we will find out maximum of minimum expected gain. Instead of actual gain or actual losses, now we are trying to get the expected gain value and expected loss value. Why the word expectation we were using? Because the strategies played by the player are along with some probabilities. Therefore, whenever we have the activities or an event is going to occur, then the outcome is, we cannot call the outcome as an exact value. It can be called as an expected value of the game, expected outcome of the game. Therefore, actually it was defined to be an expected value. Either it is a summation or integration of possible values from the random variable. Here we are not saying exact values. These are the possible values. And how this mathematical expectation is being defined? Mathematical expectation is defined as summation, the event into its probability. Okay. Therefore, here also, whenever we were going to find out the minimum expected gain by the player A, if he chooses to play first and second activity with some probability, say x and 1 minus x. As we have only two activities, let me write the probabilities as x and 1 minus x. Therefore, we will find out minimum expected gain of a player A when B chooses to play first activity. Similarly, we will find out minimum expected gain of a player A if B chooses to play second activity. Right? Therefore, we will obtain two minimum expected gains of a player A, and then player A want to maximize the corresponding minimum expected gain. Okay. Same concept will be applicable to the player B. What player B will do? Player B will try to find out maximum, or he will try to find out the expected losses. Okay. Therefore, he will find out the maximum expected loss. B will find out maximum expected loss if player A chooses to play first activity. Then second, he will find out the maximum expected loss if player A chooses the second activity. Therefore, there are two expected losses, maximum expected losses to the player B, and out of the two, he will find out the minimum. In this way, the same Maxmin min-max criteria is applicable, but instead of direct gain or direct loss, the words will be replaced with expected gain and expected losses. This is what a simple. Now, in order to find out the expected gain and expected losses, we have seen this example in detail, right? Now, this is a structure. If a player A chooses to play two activities 1 and 2 with probabilities x1 and x2, B chooses to play B chooses to play activities 2 with probabilities y1 and y2. Therefore, if B plays activity 1 only, what will be the expected gain to the player A? This is v11 x1 plus v21 x2. v11 x1 plus v21 x2. And if player B chooses to play the second activity, the minimum expected gain of a player A will be v1 to x1, v2 to x2. Here I have written. And therefore the expected gain of the player A is obtained by multiplying both these minimum expected gain with the corresponding probability. Right? And then we will find to therefore the new concept was defined, strategic saddle point. Saddle point was defined actually is the position at which we will get max min value of the game is equals to min max value of the game. Right now, max min value is equals to min max value. Here also the same concept. Min max expectation is equals to max min expectation. Is called as a strategic saddle point. This is a simple example we have seen in the last lecture. And here are the expectations, expected gain of a player A if B chooses first activity. Expected gain of a player A if B chooses to play second activity, and the corresponding probability is obtained by equating both the values. Similarly, we have found with respect to B as well. Now we were going to extend this criteria to the rectangular games with M and with two-player game with M and N activities respectively. Okay, let me just try to explain you again how we have found out the maximum of minimum expected gain and minimum of maximum expected losses. For this, let me write down player B. Suppose it has two activities. Similarly, player A has two activities. We were writing this payoff matrix with respect to the player A. Right? Now let me write the entries of this matrix be V11, V12, V21 and V22. Again, as this game is not a game with saddle point, therefore this is a game of a mixed strategies. Therefore, let me write the probability. Let us say the player A will choose the first activity with probability x1 and second activity with probability x2. Similarly, Y chooses first with probability y1, second with probability y2. So these are the probabilities of the respective activities chosen by the player A and the player B. Okay, now we will write first in case of player A. Okay, what is this player A is going to do? He will find out minimum expected gain first, and then he will try to maximize. What will be the minimum expected gain if B chooses first activity? Minimum expected gain of player A if B chooses first activity. Is that okay? What will be the minimum expected gain? This is the outcome if B chooses, if A chooses first, B chooses first activity. Similarly, if A chooses second, B chooses still same. Therefore, the expected gain will be the corresponding outcome into its probability. Therefore, let me write V11 into x1 plus V21 into x2. Okay. Then what will be the minimum expected gain of a player A? Minimum expected gain. Instead of writing minimum, what I will write expected gain only. Then we will try to find out the minimum amount it's no. Therefore, let me write only expected gain. Expected gain of player A if B chooses second activity. Okay. Now B is selected to choose second activity. What will be the expected gain? V12 into x1 plus v22 into x2. Is there any doubt up to this?
No, ma'am.
Now, whatever the expected gain player A has obtained according to the selection of activities by the player A, first he will try to find out the minimum expected gain and then he will try to maximize the corresponding. Therefore, actually what A selects to do, A selects to maximize is minimum expected gain. Correct, na? A selects to maximize its minimum expected gain. Therefore, what can I write? This is maximum of minimum expected gain. What is the minimum? This is the minimum. What's the problem to the printer? This is the minimum of these two expected gains. What is the v11 x1 plus v21 x2? Similarly, I can write the second one is v12 x1 plus v22 x2. Is that okay? And this maximum we will find out over the two values of x1 and x2. Whatever this minimum we will first find and then we will try to find out the values of x1 and x2 which will give us the maximum of the minimum expected gain. Is that okay? This is what with respect to player A we have written. Now what this player B is going to do now? Same we have to repeat. This is first let me write. Now what second we were going to write? Second we will try to find out the expected losses to the player B. What will be the expected losses to the player B? Expected losses to the player B can be obtained by selecting A chooses to play first activity and second activity. Therefore, what will be the expected loss if A chooses first activity? Is it v11 into y1, v12 into y2? According to our mathematical expectation formula, x into p of x, an outcome of event into its probability. What is the outcome of an event if both the players chooses to play first activity? v11 is an outcome. Similarly, if A chooses first, B chooses second, this is the outcome into the corresponding probabilities we have to write. Is that okay? 1 1 y1 1 2 y2 we have to write. Expected loss of player B if A chooses to play first activity. Okay, what will be the expected loss then? This is v11 y1 plus v12 y2. Correct, no? If B plays first activity, then what is the expected loss of the player B if A chooses second activity? Expected loss of player B if A chooses to play second activity. Is that okay? What will be the corresponding expected loss? Second row we have to select v21 y1 plus v22 y2. Okay. Now what player B is going to do? Player B chooses to, yes, minimizes maximum expected loss. Okay, therefore what he will do, he will try to minimize maximum of his expected losses. That is v11 y1 plus v12 y2, v21 y1 plus v22 y2. Okay, therefore our aim is to find out the two probabilities y1 and y2, which is going to minimize this maximum expected losses. Is that okay? Therefore, that idea of max min min max criteria is same. But instead of direct loss or direct profit, we were going to get the idea of expected profit and expected losses. Okay. Is this point understood to everyone? This is what I have shown for two-person game only. Now our aim is to extend the idea to a rectangular game with having more number of activities. Same criteria we were going to find out. What these two values are called actually then? Max min is V lower bar and min max is V upper bar. Is that okay? Any difficulty?
No, ma'am.
Okay. Now we will go for generalizing the idea if both the players have number of activities. Okay, therefore let me write an heading min max and max min criteria. Criteria or principle for mixed strategy games. Understood now why the game is called as mixed strategy game?
Yes, ma'am.
Because here as there will not exist a starting point, if one of the activity played by the player will not give us the optimal strategy. If the player A has to play the activities with some probability, that is all the activities he has to follow simultaneously with some different probabilities. Okay, now what we will do, we will just try to generalize this idea for player A and B having number of activities. Suppose player A is having some 1 to m activities with probabilities x1, x2 to xm. Similarly, B player has the activities 1 to n with probabilities y1, y2 to yn. Say. Now we will write the payoff matrix and also we will find out the max min max of expected loss and expected gain as we have done uh, in this example of having two activities to each player. Plus we will generalize this, right? Therefore, if these are the probabilities, what are the properties? Summation xi is equal to 1 and xi non-negative. Similarly, summation yi is equal to 1 and yi's are also non-negative. Non-negative, or one can write non-negative and less than or equals to 1 as well. Okay. And these are the probabilities, right? Let me write with respect to player A and player B. With respect to player B, if it has 1, 2, dot dot up to some yj, some j activity, 2 n. Okay. Similarly, let me write for with respect to player A. This is 1, 2. Somewhere let me write I and continue this to yeah. This is for player A. Now, as this is a game with mixed strategy, let me write the probabilities as well. And here I am going to write this is with respect to parameter I and this is with respect to parameter J. This is y1, y2 to yj and yn, and the probabilities here will be x1, x2, xi and xm. Say. Okay. How should I write the entries of this table? 1 1, 1 2, 1 j, 1 n, 2 1, 2 2, 2 j, 2 n. Similarly, here I will write vi1, vi2, vi2, Somewhere it is Vij and Vin. Last Vm1, Vm2, Vmj. This is Vm. Yeah. So this is M cross N rectangular matrix. Okay. Now what we were going to write? We were going to write the expected gain first with respect to player A. Then we will write expected loss with respect to player B. Now let me just write player A selects probabilities xi which maximizes the minimum expected gain in a column while player B selects the probabilities which minimizes the maximum expected losses. Expected loss in a row. Why we are saying it is in a row and in a column? Because whenever we were finding the expected gain of a player A, we were assuming that B plays one activity at a time. And likewise, we are going to find out all n expected gains, right? Similarly for the losses. And whenever we say that the player B chooses first activity, then we have to find out the expected gain by using this first column, right? If B chooses to play second activity, we have to find out the expected gain to the player A using the second column. Similarly, while finding the expected loss to the player B, we have to say that player A chooses first activity, and if it chooses first activity, we have to use this row in order to find out the expected losses, right? Therefore, what I will do first, I will write maximum of which values x1 to xn, correct? From minimized expected gain. What is the expected gain using a column? Can anyone tell me the entries? Column entries 1 1 2 1 m1, no? Whether it is v11 x1 v21 x2 up to vm1 x m. Is that okay? Second column is V12 X1, V22 X2 up to Vm2 Xm. Continue. We got for the last column V1n X1, V2n X2, so on, Vmn Xn. Is that okay? So let me just write it in the summation form. Okay, and this is max mean value. Max mean value means it's a lower bar, correct? No, this is maximum of all the probabilities xi, which is minimum among. First term, let me write with respect to summation. Is it summation I equals to 1 to m? Yes. Is it vi1 xi? Second, I equals to 1 to m, vi2 xi, and continue. Last is summation I equals to 1 to m, vin into xi. Is that fine? This is max min value. Okay. Similarly, can I write directly with respect to player B? Similarly, we will try to find out min max value. Min max value is denoted by V upper bar. This is minimum about the probabilities Yj. Okay, and this probability is actually found in order to maximize expected losses. What will be the expected loss to the player B if A chooses to play? If A chooses to play first activity, what is expected loss? Outcome into its probability. 1 1 y1, 1 2 y2, 1 j yj, 1 n v1n into yn. That is, we are using the row now. With respect to player A, we have used columns. With respect to player B, we were using the row now. Okay. So let me write down the expected losses. Shall I write directly in terms of summation itself?
Yes, ma'am.
Okay. What will be the summation now? Summation is now
Summation
over j
from
equals to 1 to n. Yes.
V1j X
Hmm?
Yj.
Sorry. X, no? Y we have to take. Sorry. V1j, yj, summation j equals to 1 to n v2j yj and so on, summation j equals to 1 to n v m j yj. Is that okay? Whenever the two values will get be equated, these are called as the expected values of the game. Yes, understood the criteria?
Yes, ma'am.
These values are called as, are referred as these values are referred to maximum, that is V lower bar, and minimax, that is V upper bar. Expected values respectively. Yes, if any difficulty up to this, you can ask me. Instead of loss and gain directly, it was just been written with expected gain and expected loss. And the job is to find out the values of the probabilities now. Okay. And whatever is your probability, xi will give us the max min value, will be the required optimal strategy for the player A. Whatever is the min max value for the with respect to the probabilities yj is nothing but your optimal strategies for the player B. Is that okay? Now let me just write one lemma statement here. The lemma statement tells us that suppose we have one pair of matrix. Then if we add a constant number to every element of that pair, then optimal strategies of the new matrix is same as the optimal strategies of the old one. Let me write A equals to Vij be the payoff matrix of m by n game. What is m by n game means? I told you earlier. M by n game means the player A has m activities, player B has n activities, so that the resultant payoff matrix is of order m by n. M by n game will stop if B equals to V dash ij. V dash ij is obtained from A, obtained from A by adding a constant c to every element of capital A, then optimal of the strategy of B is also an optimal strategy for A. Is also an optimal strategy for A. Is that okay? We are not going to take the proof of this actually. If you want, you can just see the proof in the book. Okay. Let me go for the next one. The main point we want to discuss today is how we were going to use this Maxmin minimax criteria of mixed strategies and those used in order to derive LPP. That is, we were going to solve these rectangular games of mixed strategies by using linear programming problem. Therefore, we will see first an equivalence between these rectangular games and linear programming problem. This is what the main point we want to discuss today. Let me write a heading: equivalence of rectangular games and linear programming. Equivalence of rectangular game and linear programming. That means we were going to now convert a rectangular game to a linear programming problem. And once we convert it to a linear programming problem, we know there are so many methods with us in order to solve the linear programming problem. Now, in order to obtain the equivalence, we were going to use these two statements. Which two statements? This one. Max mean criteria or max mean value of player A and min max value of the player B. Okay. Now here we will write first with respect to player A only. That is, we will construct an equivalence between a rectangular game with respect to player A and linear programming. Then once we establish this equivalence, we can easily go for with respect to player B. Okay. What should I write? Player A I will write. Player A. What player A is going to do? Player A is going to maximize minimum expected gains. This you have to remember, okay? Maximize minimum expected gain, and this maximum is over xi. And which part of the matrix we were using? Here we were using columns in order to find out these expected gains. Is that okay? You have to remember. Similarly, with respect to player B, this is min max of expected losses, and we were using a row in order to find out that expected losses. Therefore, don't get confused with both the players simultaneously. I will write only with respect to player A initially. Okay. Therefore, the aim is to maximize his minimum expected gain. Therefore, already we have found out this is maximum over the probabilities xi, and which will be minimum among the summation values. What are the summation values we have written? I equals to 1 to m vi1 xi. Summation I equals to 1 to m vi2 xi. Continue summation I equals to 1 to m vi n xi. Is that okay? Okay. What is the constraints on this? What are the conditions on the probabilities? As we have involved probabilities in this discussion, what are the constraints on the probabilities we know? May I write the first constant as sum of probabilities is 1? Is it okay? And what is the
Yes, ma'am.
second constant? All the
Yes, ma'am.
probabilities are non-negative. I equals to 1 to m. I equals to 1 to m. Is that okay? Now look at this structure. Isn't it the structure familiar to us? Maximizing some value which is subject to some constraints. Correct, na? What I'll do, whatever is this bracketed quantity within these rectangular brackets, we will denote it by some v as an objective function which we want to maximize and which is subject to these many constraints. Is that okay? What I'm going to substitute, let us put what I'm going to put this bracketed quantity, that is minimum of summation vi1 xi vi2 xi2 summation vin xi, and then I'm going to call this as some objective function v. Is it okay? So what this statement becomes, this one, this is maximum v, no?
Yes, ma'am.
Now, from this, look at whatever the substitution we have made. Minimum among these summations is V. Therefore, may I write any other constant as well? Because in this objective function, we have two optimization concepts, minima also, maxima also. Therefore, just to remove this minima, what I will do, as this value V is minimum of this finite set with n values, therefore, may I say, which immediately implies what is the relation between any arbitrary value of the set and V, which immediately implies that summation I equals to 1 to m vi1 xi and v. What is the relation between these two terms? Minimum of this set is v. Therefore, the
Less
relation
than.
between,
Greater than.
is it less or greater? Both the answers I got. Right? Na? Less than 1, someone has said less than, someone said greater than. Yes, what should I write exactly?
Greater than.
Yeah, it is greater equal. Let me give you one example. Minimum of the set 1 to 10 is 1. Correct? Minimum of this set 1 to 10 is 1. Then what is the relation between arbitrary value of the set and this minima? If I take 1, what is the relation? Equal to. If I take another value 2, the relation is greater equal. Therefore, if I just combine both the possibilities, this is greater equal. Right? No? Therefore, this is greater equal. Okay. Similarly, the second is also greater equal. Na? Summation I equals to 1 to n vi2 xi is also greater equal by v, and summation I equals to 1 to m vin xi is greater equal by v. Therefore, if I want to remove this minima of the set is equal to some v, I will add these as the constraints. Is that okay? Now the problem becomes, thus the problem now becomes, okay, what the problem now becomes, this is maximize v, correct, no? Maximize v subject to, what subject to? Yes, first constraint I will write this as a first constraint. Let me run up the summation over I. Let me go to next page itself. Okay, is it v11 x1, v21 x2? Column wise we were writing, no? Don't forget. Second, v12 x1 v2 x2 so on vm2 xm greater equal by v. And what is my last one? v1n x1 v2n x2 up to vmn xm greater equal by v. And the previous two constants which we have already with us. What is that constant? Sum of probabilities is equal to 1 and x1, x2 to all the variables xm are greater equal to 0. Now these are my variables x1 to xm which we want to maximize v. Okay. In book it was written actually maximize x naught is equal to v. But what I feel it is better to write maximize of v only. Right now? Because here we were directly substituting. This minimum of the bracket is v and the objective function is minimum of this bracket. So this is maximum xi I can write. Maximum of xi, maximum of v subject to xi and which is subject to the constraints. Now how many constraints we got in this? How many constraints do we have?
n constraint.
N plus 1. Good. N plus 1. And these are non-negativity restrictions. Correct, no? But the problem here is, whatever is the objective function v, the same is occurred in the as the right hand side of your constraints. Okay, correct? What's the problem? Whatever is your objective function v is given to be the right hand side of this problem. Okay, so we now just want to simplify this idea. Now in order to simplify this idea, we will try to divide by v. We will try to divide by v and whatever the new variables we will obtain, we will call them as the new variables. Later we can resubstitute the values of the variables once we find the value of v. Okay, so what the job we were going to do? We were going to divide by v. But division by v makes sense if we know the nature of v. V positive, V negative or V zero. Correct now? Nature of V. If V positive, yes, if V positive, whether we can divide by V? Yes, can I divide by V if V is positive? Yes or no? What is your
Yes,
opinion?
ma'am.
What
Yes,
is the
ma'am.
effect on the inequality then? No effect, no? No effect, we just will divide. Okay. What is the effect on the inequality if V is less than 0? Can we
Inequality
divide?
change.
Yes, we divide, but only the change will be the inequality nature changes, but still the division is possible. What for v equal to 0?
The
What for v
So,
RHS will
equal
be,
ma'am,
yes?
it gives
Hello?
infinity, ma'am.
Yeah, we cannot divide, na? Division
Yes,
by
ma'am.
0 is not allowed. Therefore, what we will do now, we are going to use that lemma we have written. What lemma says? Adding a constant to a payoff matrix will give us the optimal strategy same. Right now, and the value of game is obtained by the payoff matrix. Now if the value of game we were getting 0, then whatever is the payoff matrix we will add a constant c to the payoff matrix so that we can remove this value of v from v equal to 0 to v equal to a constant c. Is that okay? Whenever v becomes 0, we were going to add a constant c to all the entries of the payoff matrix so that the value of game changes from v equal to 0 to v equal to constant. And then division by 0 is allowed. Division by that v is allowed. Correct, no? So for anyhow, whatever is the three possibilities, now we can divide by v. Now assuming that division by 0 is possible. If I divide by 0, what will happen? The first inequality will turns to b. It will be my first inequality v11 into x1 by v, v21 into x2 by v, so on, vm1 by xm by v and is greater equal by 1. Second one, v12 x1 by v, v22 x2 by v, and vm2 xm by v and is greater equal by 1. What is the last one? v1n x1 by v, v2m x2 by v, vmn, no? Yes, vmn xm by v greater equal by 1. Also, x1 by v, x2 by v, xm by v is equal to 1 by v. We were dividing by v to this constant as well. This constant. Therefore, dividing both sides by v gives me this value. Now, all the values of the variables, now all the constants are in this format now. Now, we were going to resubstitute the variables x1 by v, x2 by v, xm by v to a new format. Let me put the values as capital X1, capital X2 and capital Xm. Now, suppose suppose x1 by v is capital X1. I hope you are getting clear difference between by small x and capital X. Xm by v is capital Xm. Okay. Therefore, the objective function, whatever we have written, maximum of v we have written. Now, may I say it becomes minimum of 1 by v as well? Why we are writing 1 by v? Because now 1 by v have with this values. Correct? So this is minima. What is 1 by v? This is x1 by v, x2 by v, to xm by v, which in turn gives us minimum of, yes, capital X1, capital X2 to capital Xm, subject to the constraints. What are constraints now? First constraint will be v11 capital X1, v21 capital X2, so on, vm1 capital Xm greater equal by 1. Second, v12 capital X1, v22 capital X2, so on, vm2 capital Xm greater equal by 1. And last is v1n capital X1, v2n capital X2, so on, up to vmn capital Xm is greater equal by 1. Now we were not going to write this one, this constraint, because this constraint already we have made using the objective function. In order to write maximum of v is minimum of the sum of these variables x1 plus x2 plus xm. Is that okay? And what about the variables? The new variables x1, x2 to xm are non-negative. Okay, now this is a linear programming problem which has this as an objective function. What is the objective function of your linear programming problem? This is your objective function, minimum of sum of variables subject to, yes, how many constraints? N linear constraints. Is that okay? How many original variables we have? M variables, no? Then what the job we will do? We will try to solve this LPP with usual simplex method, and just finally we have to substitute the original values of, finally we have to find out the original values of the variables with the resubstitution. Okay. So let me just conclude with a statement. After an optimal solution is obtained, after an optimal solution is obtained by simplex method. See, whenever, though we were writing it as simplex, but the inequalities are of greater type, we have to use some other methods as well. So for this simplex method, obtained by usual simplex method means whichever method is applicable, because all the methods begin to phase dual simplex are derived with the help of simplex method only. Original optimal values can be obtained from the given transformation formula. It is resubstitution. Is that okay? This is all we have written with respect to player A. Now it's a time to write down with respect to player B. Now what we were going to write? We were not going to derive everything again. We will write on the other hand, similarly if we derive for the player B, then the linear programming problem will be. What is the linear programming problem? Proceeding to the same manner. This is maximize sum of the variables y1 plus y2, capital, okay, capital Y n, subject to. Now here we were going to use row, therefore it is simple to write v11 capital Y1, v12 capital Y2, so on, v1n capital Yn less than or equals to 1. This will be less than or equals to, no? Why it is so? Because actually the objective function in this is minimizing maximum losses. This is minimum of maximum summation v1j summation v2j summation vmj. Therefore, if I keep this as an objective function v, then this is maximum of this bracket is equal to v. Therefore, what kind of relation is going to be there between this arbitrary number and v? Maximum among this set we are calling as v. Correct, no? What is the relation? As of here we have written less, greater, equal. Here we have written greater, equal, no? Because minimum of these values we have kept as v. But here we were substituting a maximum of these constant is equal to v. Therefore, relation is going to hold as less equal. Okay. Instead of player A, with respect to player B, it will be easy for us to write, na? I don't know how many of you are getting me. I'll try to give you a very simple, I'll try to explain a very simple manner. What for y naught? Our objective function is 1 by v. Capital Y1 is small y1 by v. Capital Y2 is small y2 by v. Capital Yn is small yn by v. This is the equivalence or the relation between a rectangular game and a linear programming problem. If you have any difficulty until this, you can unmute yourself and ask me. Okay, in the next lecture, we will take a problem on this. If I take the example on this, the idea will be very clear and it will be clearly known how the rectangular game without saddle point can be solved by using the linear programming problem. This is the first method we were using in order to solve the games without saddle point, that is with the help of linear programming problem. Yes, I hope there are no difficulties in this. If you have, you can just unmute yourself and ask me. Yes, students,
No, ma'am.
no difficulty. Let me stop for today then. Let me stop for today. Thank you for being with me for this lecture. Thank you.